Okay, so what I wanted to finish off on was taking a look at a couple of synthesis problems. Because in order for you to master anything or to master the content in this class, you really have to master all of the reactions, okay? There's no way to get through this class without mastering all the reactions that we learned. Now, let's say you wanted to take this compound here. This is called isobutylene, or you could call it 2-methylpropene. If you treat that with bromine, that's going to add 2 bromines, one on each of the carbons that was in the double bond, to make this dibromo compound. And we know that this occurs by anti-addition. It's not important here because you end up with no stereocenters in this case, but that's something that you want to know. So what that means is that you've got to know all the different reactions that we learned in this class. Now here it says, identify reagents that can be used to accomplish each of these transformations. If you're having trouble with the reagents, these reagents are going to be found in chapter 8. So all the reactions in here are chapter 8 reactions, and I just want to review them with you. So let's start with, why don't we start with this one right here? So we'll start with this reaction here where we're trying to make this compound from 1-methylcyclohexene. So could anybody tell me this reaction, would that be the Markovnikov addition of HBr across the double bond, or would that be the anti-Markovnikov addition of HBr? Where I have that blue arrow. Yeah, absolutely. Absolutely. All of my students are 100% correct. They said it's Markovnikov, so Markovnikov addition of HBr. And so for that, we just need HBr. Now, if we go counterclockwise to the next reaction, we have an anti-Markovnikov addition. So this is anti-Markovnikov addition of HBr. So for that, we need HBr, and we need to have some organic peroxides in there. And that's a mechanism that we would have covered in chapter 10. We covered the initiation, propagation, and termination. Let's scooch way over here to the far left. And this reaction here where we want to do a bromination of an alkane. So we're starting out with an alkane. This is this is methylcyclohexane, but either way, it's an alkane. And then we just want to add bromine. Could anybody tell me what the conditions would be for this reaction? Yeah, thank you. It would just be bromine and light, wouldn't it? So we're just going to put bromine and light. Okay, so that would be a chapter 10 reaction. And then the next one is an elimination going from here to here. And we're making the Zaitsev product, so we want to use an unhindered base. So let's choose something like sodium ethoxide or sodium methoxide. That would work totally well as well. Okay, so that's just an E2 elimination. So we'll put here E2, and then we'll say we're making the Zaitsev product. I'll just put it in there like that. Okay, next one, we're doing the Markovnikov addition of water across a double bond. And so for that, we're just going to use aqueous acid. You could either write H3O plus, that would work. If you were to write H plus in H2O, that works. If you wrote H plus, if you wrote sulfuric acid and water, I would accept that too. Any of those are good, but I'm just going to leave it simple, H3O plus, so hydronium. And the next one, so again, this is a Markovnikov addition. The next one is anti-Markovnikov addition of water across a double bond. And remember, that occurs with syn addition. So this is syn addition of the hydrogen and the hydroxyl. And that's a two-step process. The first step is borane and THF. And the second step is hydrogen peroxide, H2O2, and sodium hydroxide. So that's hydroboration oxidation. Next reaction is we're just taking the alkene and converting it to the alkane. So for that, we need nothing more than hydrogen gas, so H2, and palladium, platinum, or nickel. Either one is fine. The next reaction, we're making the dibromo compound, and this proceeds via anti-addition. And so for that, we would just use bromine, Br2, nothing more than that. If you want to, it's not light because it's not a photochemical induced reaction. If you want to put a solvent like dichloromethane, that's totally fine, but you don't need to do that. I'm just going to make it simple since the final exam is only a day or two away. Next one, this is what we call a halohydrin. So a halohydrin. And a halohydrin addition is done using bromine to make the bromonium ion, but then instead of using bromide as a nucleophile, we use water as a nucleophile. And so we have bromine and water to make a halohydrin. The next one is the anti-addition of 2 hydroxyls. So that's anti-addition of anti-formation of a diol, I guess is what you'd call it. So the first step for that was a peroxy acid. You can write RCO3H. You could also write MCPBA for metachloroperbenzoic acid. That works too. And then in the second step, after you make that epoxide or oxirane, you crack that open with aqueous acid. The next one is a syn dihydroxylation. So we're adding 2 hydroxyls on the same side. We were just looking at this a minute or two ago, and we said, okay, well, you can do that with potassium permanganate in base. That works. And there's nothing wrong with that. You can also use osmium tetroxide and sodium sulfite or sodium bisulfite. But the most commonly used way is to use osmium tetroxide, just a catalytic amount of it because it's so toxic, and N-methylmorpholine N-oxide, or NMO, as a co-oxidative. That brings us to the last one where we have the double bond and we want to cleave that. Could anybody tell me what the first step for that one would be? It's a 2-step process. Even if you can come up with both steps, that'll work. So this is called ozonolysis. Yeah, thanks, Nicole. Yep, absolutely. It's ozone for the first step. Does anybody know the second step? There's a couple of things we can use. Yeah, DMS is most common. You can also use zinc and water, but I like dimethyl sulfide. It's a lot easier to remember. Now, a question that students come up with all the time, if they, forget, things that you need to know. But I'm going to highlight all the mechanisms that you need to know. So I'm going to write here, no mechanism. Okay, so anything that yellow. So for the Markovnikov addition of HBr, you need to know that mechanism. This anti-Markovnikov addition of HBr, that's a mechanism that we looked at in chapter 10. So we'll say here mechanism was in chapter 10 because it wasn't covered in chapter 8. Also, this is another mechanism that was covered. Oops, where's my highlighter? This mechanism was covered also in chapter 10. So that's just bromination. You need to know the mechanism of an E2 elimination. You need to know the mechanism of Markovnikov addition of water. Hydroboration oxidation, not going to ask you about that mechanism, so you don't have to know that one. Hydrogenation, I mean, you need to understand that it's an addition. I would probably want to know that both of the hydrogens are added to the same face of the molecule, but I'm not going to ask you directly, draw the mechanism of hydrogenation. The mechanism of bromination, yes, that proceeds through the bromonium ion. The mechanism of halohydrin formation, yes, it's the same as bromination, except the nucleophile is water instead of bromide. The mechanism of the formation of the transdiol, no. It's something that's covered in the textbook, but I don't ask my students about it, generally speaking. The next one, osmium tetroxide, no. And ozonolysis, no. So the ones that I have the yellow check mark by, these are the ones that I expect you to know the mechanism of. Any questions about those? Give me a thumbs up if you're like, I think I know, I'm like 90% of the way with these reactions. I'm 90% ready on these. Awesome. Awesome. Remember, let me encourage you. If you're like, oh, yeah, I'm 90% of the way, Mr. Dion, but I had to work really hard to remember that. Well, number one, that's normal. Everybody has to work really hard to remember them. But just remember, all that hard work that you put in this semester, it's going to help you in the second semester because these reactions will come up over and over again in that class too. It doesn't matter who you take organic chemistry to with. If you take it at another university or college, these reactions will all come up, okay? So it was not for vain, okay? It wasn't for nothing. Okay, let's take a look at the next question, 11.2. It says, identify reagents that can be used to accomplish each of the following transformations. If you're having trouble, the reagents for these transformations appear in the review of the reactions at the end of chapter 9. So this is a real chapter 9 based question. So that's the Alkynes chapter. And yeah, it says first you should try to identify the reagents yourself without any help. Well, let's see here. I mean, there's a bunch of places we could start. Why don't we start here? If you're taking propine and you want to add HBr across it, well, all you need is HBr, really, nothing more than that. But I would just be cautious, and I would write HBr, and then I'd put just one equivalent. So everybody knows I only added one molecule of HBr. Right, same thing here. If you're going from this compound to the dibromo, I would also write HBr, and I would put one equivalent like that. All right, so I put this like that. The next one, both of these reactions are identical, whether it's this one or this one, they're both the same thing. This is a geminal dihalide, so geminal, like Gemini for twins, and this is vicinal. So we've got geminal and vicinal. Either way, if you want to eliminate both of those bromines, deprotonate and then protonate, it's the same conditions. You use excess sodium amide in the first step, and then in the second step, you would just use H3O plus, or water would work, but it's the same thing no matter what. So we'll just put excess, excess NaNH2, and 2 is H3O plus, like that. So there we go. Oops, I didn't mean to do that. I got a little bit ahead of myself there, didn't I? Okay, where was I? Somewhere around here. Next one, let's do the ozonolysis. This one here. So the first step here is ozone. Does anybody remember what the second step for ozonolysis was? Ozonolysis of an alkyne. So if you break that bond. Yes, thanks, Nicole. Absolutely. So it's just water. Yep, perfect. Next one is if you want to make a tetrabromide, so just brominate everything, I would just write bromine and I would put excess or excess bromine. Either way, it doesn't matter. So just you're brominating the hell out of it. Whereas this one, you're only adding one equivalent of bromine. So I would put bromine and I would put one equivalent because you're only adding one molecule of bromine. The next one, going from propene to 2-butyne, this is something that we looked at already during our practice this morning. So the first step was sodium amide to deprotonate, and the second step was methyl iodide or methyl bromide or methyl chloride. We'll just put methyl iodide. Let's take a look at all these different reductions over here. If you want to make the cis alkene, you've got to use hydrogen and Lindlar's catalyst. So Lindlar's catalyst. The next one, if you want to hydrogenate completely, you would just put hydrogen and palladium, platinum, or nickel. And the next one, we want to make the trans alkene. We looked at this also this morning. My students knew that really well. So that's sodium and liquid ammonia, if you want to put the liquid phase there. Okay, so we've got all those reductions. 2 reactions left. The next one is to make an aldehyde, and that comes from an enol. Right, that would come from this enol. And this enol will undergo tautomerization to give you the aldehyde. So what are the conditions? Well, instead of using borane in THF, use a hindered borane like 9-BBN in the first step. And then in the second step, you use H2O2 and sodium hydroxide. And the last reaction is, making a methyl ketone. And that would come from this enol which undergoes tautomerization to give you a methyl ketone. So for that, we would use sulfuric acid and water and mercuric sulfate, HgSO4. And there you have it, my friends. So those are all the reactions that you would want to know from chapter 9. Now, in terms of mechanisms, I'm going to highlight this. The mechanisms I think you should know, would be the double elimination. Those are the same. Okay, so you'd want to know those. This mechanism of the alkylation you'd want to know. And really, those are the only ones that you would really be asked about. You should understand the radical ion here, I guess, so that you know why you get the trans alkene, but there's no other mechanism that you would be asked to draw. Okay, we looked at some of the rationale for some of these before, but that's about it. Let's just see if we could solve a couple of these problems here. It says propose an efficient synthesis for each of the following. If we wanted to solve A, we're taking this alkene and we want to make an alkyne. Well, if you remember retrosynthesis, it's basically saying, well, I'm not changing the carbon skeleton. Here I have 6 carbons and here I have 6 carbons. So the only way I would know how to make that alkyne would be from this vicinal dibromide, which I could make from the alkene. And we have the alkene. And so the synthesis of this alkyne would be to first treat the alkene with bromine to make the dibromo. And then 2 would be to treat it with excess sodium amide. And then 3 would be to treat it with water or acid to add the proton on the end. All right, so that's how you want to approach a retrosynthesis like that. The same thing would apply for the next one. If you want to have your bromine here, right, that would come from the Markovnikov addition of bromine across, this double bond. So then the question comes, well, how do we get from here to here? Well, we would want to use some kind of base to do an E2 reaction. You'd want to rip off this proton, so you'd have your base, which would pull this proton off, make the double bond, and you would lose your leaving group. So what's your base going to be? Well, you want to use a base that's going to mitigate substitution. You want to do something that's only going to do elimination. So you could use DBU, DBN. You could use potassium T-butoxide. I'm going to choose DBU. So, and that would, again, suppress any kind of substitution. So DBU, it's a non-nucleophilic base. And then to do the Markovnikov addition across that double bond, you would just use HBr like that. The next one, we want to make a double bond here. So we're basically going from a Hoffman alkene to a Zaitsev alkene. Right, so if we think about retrosynthesis, if we had this bromo here, right, then we could rip off this beta proton using sodium methoxide or ethoxide to make the desired alkene. So the first thing we're going to need to do is a Markovnikov addition of HBr to make this compound. And then we would just treat it with sodium methoxide. I'll choose that. All right. And then the last one is in the same vein. We know that we can make this from this tertiary bromide. Okay. So how are we going to make that? Well, we're going to take this compound and we're just going to treat it with bromine and light, like that. And then in the second step, we're going to treat it with sodium methoxide again. And that's going to give us the desired product.